In this video, we're going to be covering another chapter 16, so chemical dynamic equilibrium worksheet. And let's get started on the first question. So determine the value of Kc for the following reaction if the equilibrium concentrations are as follows, and they give you a bunch of concentrations. So the expression for Kc, this is basically just the equilibrium constant. So I'll put Kc is going to equal the reactants, or sorry, the products, which is going to be the concentration of Hi squared divided by the reactant. So H2 to the 1 power times I2 to the 1 power. Once we plug in our equilibrium concentrations in the expression, we get 1.6 squared divided by 0.14 times 0.39. And I'm not going to solve for that, but I'll let you guys do that on your own. So now looking at 1b, to the system at equilibrium, 0.25 molar of H2 is added. What are the new equilibrium concentrations of all the species? So write the expression for Q. So now Q is basically the same thing as the equilibrium constant, but not at equilibrium. So it's calculated the exact same way. So to the system, 0.25 molar of H2 is added. So originally at equilibrium, our H2 is 0.14 molar. Now we're going to add 0.25 molar to get our new concentration of H2, which is 0.39 molar H2. So we can write our expression for Q, even without knowing that information. We can write Q as being the same thing as K, really, but not at equilibrium. So we're going to have our concentration of Hi squared divided by concentration of H2 times the concentration of I2 at a specific point. Now calculate Q with the new concentrations. So you would have Q equals Hi doesn't change at all. So Hi would be 1.6 squared divided by H2. Our new H2 is 0.39 times our original I2, which didn't change either, 0.14. And that would be the value for Q. And then determine the direction of the equilibrium, meaning determine which way the reaction will go in order to restore equilibrium. So what we can do is we can look at Le Chatelier's principle. And Le Chatelier's principle says that if you look at the equation right here, what we're doing is we're adding a reactant. So once we add a reactant, in order to relieve that kind of pressure, and in this case, since it's a gaseous reaction, the literal pressure, in this case, we would have to go in the direction of the products in order to relieve this kind of reaction pressure. So don't think of it as total pressure. That only relates to volume, but think about it as kind of like a scale, right? Which I've said in one of my previous videos where we talk about Le Chatelier's principle as a balance between the reactant amount and the product amount. So at equilibrium, all the amounts are not equal, but they're at a satisfactory level for that specific reaction. But if you add, let's say, to the reactants, like in this case, what you're going to do is the reaction will have to shift, and the forward reaction, in order to create more products, will have to be more prevalent. So H2 increasing will make the reaction shift to the right. Now, for 4, do you need to calculate Q, or can you use Le Chatelier's principle in this case? Now, we just use Le Chatelier's principle. And if so, how? We just explained how. But you could also use Q, because if Q is, in this case, Q would be lower than K, because you're increasing the value in the denominator. This means that the value of Q would be lower. For Q to be lower than K, that means the reaction will have to shift towards the products in order for Q to be raised to the level that K is, in order for Q to equal K at equilibrium. So that's another way you can use that. You can use Q, or you can use Le Chatelier's principle to determine the direction of a reaction. Now, knowing the new concentrations, we can calculate the new equilibrium concentrations of all species, as this question is saying. So I'm going to write the ice chart. So initial for H2, we now have our new value of 0.39. For I2, it is 0.14. For HI, it's 1.6. Now, since we know the reaction will go in the forward direction because of our increase in reactant. We now know our change is going to be minus for our reactants. And for our product, since it has a 2 coefficient, it'll be plus 2x. Our new equilibrium will be 0.39 minus x for H2, 0.14 minus x for I2, and 1.6 plus 2x for HI. Now, knowing these equilibrium expressions, we can now solve for solve for x, because we know our value of Kc. Now, Kc does not change when you add or remove products or reactants. So our value for Kc, let's say here it's y, whatever we got for number 1, we would have y equals 1.6 plus 2x, which is the concentration of the new equilibrium concentration of HI squared, divided by the new equilibrium concentrations of both H2 and I2. So what we would do is, once we get the value up here for Kc, which would be the same throughout this entire problem, unless you change the temperature, but we're not doing that here, you can solve for x. That x can be used to be plugged into each of the equilibrium concentrations for H2, I2, and HI in order to find the new equilibrium concentrations of all species. So next, once the system is at equilibrium, the volume of the vessel is decreased at a constant temperature. What happens to the equilibrium and why? So this is, again, Le Chatelier's principle, but relating volume in gaseous reactions only. So the only place where volume has an effect on the position of equilibrium or the prevalence of the forward or reverse reaction is during gaseous reactions only. Because if you have a beaker with liquids or aqueous solutions in it, it's not going to change which way the reaction goes. But for gases, it is, because we have pressure, which is explained very well in Boyle's law, or the relationship between volume and pressure, inverse. So if we are decreasing the volume, right? Decreasing the volume, that's the same thing as increasing the pressure. So if we increase the pressure, that means our reaction mixture isn't going to be what we call kind of happy. In order for it to be happy, that pressure is going to have to be relieved. In order to relieve that pressure, the reaction will have to go in the direction of the least amount of gas moles. And the reason why is because the number of gas moles directly correlates to their pressure. Because remember, from Chem 1, we learned about the mole fraction and the partial pressures and Dalton's law of partial pressures. So the number of molecules directly correlates to their partial pressures. And since they're ideal gases, their sizes are basically negligible when it comes to pressure. The sizes of each individual gas molecule, I2 is so much bigger than H2, but the distance between the molecules is so large that their size is negligible. So anyway, we have the pressure increasing. In order to relieve this pressure, the reaction will have to go in the direction of the least amount of gas moles. Now, in this case, we have 2 gas moles on the left and 2 gas moles on the right. We're at a standstill, right? We have no net delta N, so no change in moles. This means nothing will happen. So the reaction equilibrium will not shift in any direction because there is no difference in gas moles from product to reactant. So the reaction will just have to accept the fact that it has a higher pressure. So that's enough for this video. And if you have any questions, please leave it down in the comments, and be sure to like and subscribe.